Hey guys, what's going on? It's Danny, and today we're going to be talking about a sorted collection. This is going to be the start of a not short series, but a series where I'm going to talk about a lot of different data structures and the implementation of them. This is going to have more of a, ground level focus. It's going to talk about the actual implementation of the methods, the complexity, and how we got there, and how these structures are designed. And I guess the goal of this is to help you understand better what these data structures are using, how they work, how to design your own, and how to be able to understand the methods better and be able to apply the complexity of these to whatever you're doing. This is going to be the first part. I think in this series I'm going to have two parts. I'm first going to talk about the ground level, and the second part is I'm going to talk about, LeetCode or actual algorithmic applications. So stay tuned for a video on that. But to start talking about the sorted collection right away, I want to talk about the structures ADT, or the abstract data type. And so basically we're going to talk about the general, idea behind a sort collection and what it truly is. And there's a couple, key methods that would define it. But to define it in just words, it's basically a collection. That's what collection is. A sorted collection where whenever you're adding elements, it automatically sorts them. So whatever elements you're adding, it'll automatically sort them. And this can be useful for all kinds of things. But to talk about the operations, the first operation is add. And this operation is just adding an element into the data. Then there's remove, where you just remove an element. Find, which finds the index or location of an element. And this is very useful, which is something we'll get into in the actual ground level code, which we're about to look at. We also have the size. This can often be stored in a field or something, which will have O of 1 complexity. Clear can also be O of 1. You can just reassign references. It's a lot. Excuse me. And then minimax, sometimes these structures will have a way to return the greatest or the least value inside of this collection. But to talk about to take a deeper dive into the methods that I think are really, really key to the the data structure, would be the find method. The find method is what tells you where things are inside of it. For adding and removing, it's extremely useful. And to get into the complexity, for linked list, it's O of n complexity. And this is because to find the element you're looking for, you have to access each node. Starting ahead, you have to access each node, going up and down until you find it. And there's no way to really skip around. It's just you have to look until you find it. Then the second, the array version of this is actually O log 2 of n. And this is because of binary search. In a sorted array, you can use binary search to keep halving the window size to find your element and hone in on where it is. And at first glance, these complexities may seem extremely useful. It may seem like the array will have way better complexity than linked list overall, but it gets a lot deeper than that in the end. And that's where we get to the add. So the complexity of add for linked list is O of 1, because once you find where it goes, you're given the previous list node. You can just set the pointer from that list node into the element that you're adding, and then the element that you're adding, you can set that pointer into what was previously after. Now, for an array list, this is a bit different and a bit more complex, because when you add an element, you may know where it is, but all these elements actually have to move down. An array has static size, which means it doesn't change, and in order to change, you have to kind of declare a new array and move everything down, which is quite inefficient, and that's how you get O of n complexity for this operation. Next up, we have the remove, and for linked list, this is O of 1 operation, because when you're given the index of the element, you can just set that element to null and then skip over it with pointers. And this is O of 1 complexity, which is quite useful. And for an array, it's O of n complexity, because when you remove an element from array, once again, it's static length, so you have to move all the elements down. And one very important thing to note is that the find operation plays a heavy role into this, because yes, removal in addition to a linked list may be O of 1. That's only because you're setting references. In order to actually find in the first place, it is big O of n. So the complexity of these actually match up quite well, and there's not any crazy advantages to the others, but they each have their own niche uses, I guess. Now, to dive into the exact minuscule code, we're gonna dive into it over here in JGrasp. So this assignment is partially for a university course I'm taking on data structures and algorithms, and as part of that, all my coursework is on my laptop and not my home PC. So I didn't want to re-download all everything to make it work. The book libraries, reconfigure JGrasp and all this other stuff. So I'm just gonna screen share from Discord, and I hope that works. And then I guess another thing to note is, or we'll get to that later. But yeah, so to dive straight into the code, the first thing I want to talk about is the sorted linked collection, and we're going to talk about the find element. So for this, I have a extension. So my sorted linked collection extends linked collection, and when you extend a class, it means you borrow or through the process of inheritance and object-oriented programming. Yeah, you can actually access the elements from above, and this is something I'm sure many of you know because some of you completed CSA, but if you haven't, that's kind of the concept. So the first operation I want to talk about is, where is it? Find, and the find element is, I guess, in the linked collection, it's not quite as important because I don't think I actually use it, but it has a return type of void here because it's simply making sure that it exists. Because it's kind of difficult of what you would exactly return for this. You could return a previous element, and that's kind of what this does right here. It sets the previous equal to location, which is stored in memory here. But that's actually something I ended up not using in my implementation of it, which I guess is something I could have included, but I ended up just re-implementing the find on my own because I find that to be a more straightforward approach. But it would be, I guess, more straightforward and make more sense to use the find method. But to talk about the add method, which is right here, the way the add method works is you have your new node that you're trying to add into your list right here with the element as an argument, and then you have the current node and the previous node. And the first thing you do is you want to loop through every element in the linked list and find where does this belong. And this is by making sure that the current node, the node that you're looking at, is not null. You don't want to be at the end of the list, front of the list. You don't want to have that issue. And then the other condition for this loop is making sure that, I guess, the element is not where it needs to be. If the element is still greater than the element you're comparing it to, you need to keep moving it forward and forward and forward. And that's what this does. But it also stores the previous node. So it stores the previous equal to current, and that can give us the index that's pointing to where we want it to go. So once this loop terminates, we are given previous, which is a list node that is right before where we want to insert our element. And this is quite useful because, as you can see, using this element, we set the new node, we set that to the element that's after, and we set the node of previous to the one before. So we have our previous, and we have our, I guess, current node, and then right in the middle, we slide in our new node, and we point it here, and increment num elements by 1. Something small to note, I guess, of this is that if the previous is equal to null, this means that, in this case, the element that we're trying to insert will be the smallest element, so we account for that here. And then to talk about some preconditions and some things that are required for this, the pre and post conditions for this operation would be, I guess there aren't really many, but you need to make sure that you have your collection, and there aren't really many, but then the post conditions would be that you have an element added to the array. Then to talk about, where is it? Oh. No, it's not here. It's in my is it in VS Code? Let me double check. Remove. Yeah, I guess it is. So the remove element method is in VS Code because the reason why we had to implement add in the JGraphs is because when you're adding an element to a sorted array, or a sorted linked collection, sorry, that's different than removing an element, because when you add an element, you have to account for the order it goes in, which is what this logic does. But when you're removing an element, all you actually have to do is you're just setting a bunch of pointers equal to null. And yeah, so basically the first thing that you do in a linked collection is you have to find where the remove element is. You have to find where the element that you want to remove exists, and then once you find it, you have to set the values around it equal to null, and then allow it to skip over. So I guess to talk about it line by line, first of all, the first thing you're checking is if the head is equal to the location, because if the head is equal to location, you're just removing the first node, so you're just going to remove the first node by setting it equal to what's next. So the first is now the second, first one's out of here, it's gone. Otherwise, if the first node is not where it is, you need to set the previous node, you need to skip over what it's looking at. So the previous node is what's looking at your current node. So we're going to take the previous node that's looking at your current node, and we're going to skip it over the current node, which is what this previous.setLink to the location.setLink. We're setting the previous node to the location after the element we want to insert. Then to talk about, then you, I guess, decrement num elements. And then that, I guess that's the two of the main operations of add, find, and remove for a linked collection. But now for a sorted array collection, it's actually a bit different. So this is directly imported from the book. That way I can talk about it quite closely. As when I was originally looking at the compile tool, compiles. Oh, what? Oh no, I'm compiling the class. Hold up. When you compile my main method, I was originally having an issue. Yeah, it says object names and declare types unknown, and this is something I really wanted to talk about because I feel that by stepping through each individual operation, I'd be able to better explain exactly how they all work. And this is something I actually plan on coming back to. So in one of my later videos, I may come back to talking about the sorted collection, stepping through each operation slowly using the debug tool. But because we're unable to, I'm just going to step through the methods from the classes that we provided. So then, yeah, so this is the class for the sorted array collection. And the first operation we're going to talk about is... Oh, wait, this is the main method. Sorted array collection is right here. We have the two, I guess, constructors. Those aren't crazy important. But the first one I want to talk about is find, and that uses toTarget. And as we talked about before, the complexity for find in a... Check the battery. Oh. Yeah, we're good. To talk about the complexity for finding an element in an array is O log 2 of n, and this is because of binary search, which you can see here. This actually calls a helper function called recursive find or recfind. And this right here, this is, I guess, just exactly what binary search is. I'm not going to get into the exact implementation of binary search, but the basic idea is that you have a middle element, which is calculated by the first plus the last divided by 2. Uh-oh. It's not good. The first plus the last divided by 2. When you get to the middle, then you're going to see if the element that you're searching for is greater or less than. If it's greater, you move the window here, so that way it's contained inside of it. And you keep finding the middle, shrink it, middle, shrink it. You keep shrinking it and shrinking it until you actually hone in on the element exactly. And this is O log 2 of n complexity, which is quite useful, but it does kind of get, not negated, but it's unfortunate that the add and the remove have big O of n complexity, so not often will you be able to access this O log 2 of n, unless you're simply searching for the element. Now, in terms of adding an element to the array, the first thing you do is you have to, I guess, so right here, this is important. So if this is what gives it O of n complexity right here, the fact that you have to enlarge the array by 1 and copy all the elements over is quite inefficient and not something you really want to do. But then what this code does is it basically sets all the elements, it repopulates the array, and then it sets the elements at the actual location that you want it at, which you found through the find method, and it just adds it. And some of the preconditions for this are that, or I guess there's not really preconditions, but the post condition would be that you have one element added to the array after the case. I mean, I guess some technical precondition would be that the element's not null or whatnot, but yeah. So then to talk about the remove method, first in a sorted array, it finds the element, then it checks if the element's found, which is what this guy tells you. You're going to iterate through the array, find the element at, find the element that you're looking to remove and set it equal to null, and then you subtract the number of elements. And this is O of n complexity, or for sorted, yeah, it's O of n complexity because you have to actually repopulate the array most of the time, which I don't think we actually do here, but in terms of like the resizing and whatnot of everything, it's gonna end up being O of n eventually. But you can leave this empty space in the array, but this kind of can kill space complexity sometimes compared to time complexity, but that's a topic for another day. But then yeah, so that's the general, I guess, methods for the sorted array list and linked array list. Unfortunately, I was not able to debug, and that's something I hope to go over in the future. But aside from that, I'm just making sure I have everything I need. Oh yeah, so to talk about the parameters and special cases, I think I briefly touched on some of the special cases and parameters. Let's make sure the battery's good. Yeah. The first special case, so for find t, the special case that you need to consider I guess if the array is empty, then if it's empty, then you're not really returning anything. You're just returning false, or you're just saying found to false. Excuse me. And otherwise, the recursive find is what will set this found back to true, right here. But otherwise, if the array is empty, this statement will value to false, and then the found will just say false and not found. And then in terms of the parameters, except for element, it just accepts the element as a parameter. and it returns nothing. For the add, it takes an element as, and I guess the parameter is kind of obvious because that's what you need to add, and it returns a boolean true or false based off of whether or not you actually added the element. Some important things to consider are if the array already has some room for the elements inside of it, and I guess it can ruin space complexity sometimes by not always resizing it every single time when you're removing elements, but in the end, it's really not that deep, you might say. But then to continue through with the remove, or are there any special conditions for the add? I guess the precondition is that, yeah, element is comparable to previously added objects, but I guess the reason I didn't exactly touch on that sooner is because most of the time when you're using this with a generic data type, you're going to be adding elements of the same type that are easily comparable, and if you're adding elements that aren't comparable, that's a pretty extraneous use case. But then, talk about, I guess, more extraneous use cases, we get to the remove function, and this returns a boolean true or false whether or not we found the element and a target to remove, an element of a target of type element to remove. And I guess the first kind of check or extraneous case is that if the element is not found, then it kind of skips over this whole if statement and just returns what's found, which is like false. It was not found. Yeah, and then if no element returns, that's the extraneous case for this one. Then that's it for the sorted array collection. Then to talk about the sorted linked collection. For the add operation, there is the parameter this takes is an element, and it just returns a boolean true or false whether or not it was added. And the unique case, which I think I slightly touched on, but I want to really explicitly touch on this, is that if it's the smallest element in the array right here, that's what this checks for, it'll appropriately account for that by just skipping over the smallest element. Then to talk about, I think the other two are in the, yeah, these good. So then to talk about the other two operations to link collection. And once again, the class in the other thing that we were looking at is, or jgrasp, the other thing we were looking at extends this class. So all these methods are inherited by the other class. And that would include the remove, which takes a argument of type target, and then returns true or false whether or not it was removed. The extraneous case here is, yeah, if it was found, it will return false if it's not found in the array. And then the find method in the linked collection, if I can find that. The find method, it doesn't have any crazy cases other than if it's false, or I guess if the array is empty, then it would just return false. It doesn't exist in the array. But then, yeah, I think I override the add here. Yeah, I think we covered that. So then, yeah, so there's not that many extraneous cases in a lot of these, but a lot of these things are important to consider. And I think that if you're using sorted collections and a lot of these data structures in your daily use, it's really vital that you understand what exactly is happening inside of these, how the different implementations work, when you should use each, and just everything about it. So yeah, that's going to be all for today. Stay tuned for another video on other data structures and the algorithms behind this one. Thank you and goodbye.